Hello, I'd like to derive some equations that describe simple harmonic motion, specifically the equation for the position of an object, its velocity, and its acceleration. So one of the best ways to do that is to recognize that there's a connection between simple harmonic motion and uniform circular motion. And so let me show you what some of these are. So I'm going to start by drawing a circle here. Actually, I don't want to draw it there. Let's draw it over here. I can get at it. That's close enough. And then, and so this would be the path of an object going around a circle. And then I'm going to, down here, I'm going to put an axis, an x-axis, and show how an object that's oscillating back and forth along this axis is related to an object that is moving around in a circle. So, what I'd like to do now, let's switch to a different color here. Is suppose that I have an object that's right here at this point of the circle, and I'm just going to shade that in, and it's moving around that way. Now I can project the horizontal position of this object down onto this horizontal axis below, and if I just go straight down like this, I would say that when the object is at 3 o'clock position on the circle, which is traditionally where we start the angles, if that's the circle right there, the center of the circle. And then as it goes around, it eventually will get over to this point, which is 9 o'clock on the circle. And if I project that down here, we see that these two positions are the extremes at which this object will move along the x-axis. It's never to the right and never to the left of that. So if I project the center down, I get a position right here that I'm just going to call x naught. And that is the equilibrium position for simple harmonic motion. This is the position this object oscillates back and forth, left to right. It's always going around that. Never goes further to the right than this, never goes further to the left than that. So on a circle, we would say r is the distance from the center, of course, at any point on the circle. And so from x naught to this position, we would say is a distance of r. All right, we're just going to call it x for right now, and this would be minus x. And this distance from the equilibrium position to the furthest position it oscillates, the furthest displacement away, we call the amplitude. And so I'm going to label that as saying x equals a. Now, notice that a is equal to r, the radius of the circle. On this side, this position is equal to the opposite of a. So the object is always oscillating between a, negative a, and a. So the position of the object in simple harmonic motion is always going to be between negative a and a, right? And so let's suppose now, so I can pick a little different color here to work with. Let's suppose that this object has gone around a circle to this point right there. In doing so, it would go through an angle of theta. And if I were to drop this down to my axis, I would see that it is now right there. So that's about where this object is. And its position, x, is measured from the equilibrium position. So this right here in the circle, this is the position of x. That's what I'm looking for. And we see that that is part of this triangle. This would be y, but we're not interested in that. And this is r. And so on the triangle, x is equal to r times the cosine of theta. However, we know that r is equal to a. And so this is equal to a cosine of theta. Now, this would give us the position of the object along this horizontal axis as a function of theta, but I'd like to get it into a function of time. We don't often think about what angle it's at, but rather how long it's been oscillating, especially if we know the initial position. So to get to that, we consider the fact that we know that looking at our uniform circular motion or rotational kinematics, we remember the equation that theta is equal to omega times t. So it's part of a larger equation, right? Plus theta naught, right? So this tells us if we know the angular frequency or the angular velocity of an object moving around a circle, that's in radians per second, and the time it's been moving, and the angular position it started at, that theta would be given as omega t plus theta naught. But we're going to assume that that is 0 radians. So we get theta equals omega t. Now I can substitute that into this equation. X equals a times the cosine of omega t. So now, if we know the angular velocity of the object moving both in simple harmonic motion but in a circle, and the time, then we can find its position. But when you're looking at something moving back and forth along a horizontal line, could be a vertical line too, but we don't often think about its angular frequency. And so we want to be able to move that into something that is a little easier for us to understand. And so we know that omega, and if we use the same equation again, that omega is equal to delta theta over t, right? So if it's moving around a circle, all the way around the circle, in a period of time of t, we know that it goes through 2 pi radians in t seconds, where capital T is the period, the time to go around once. Now, it's often a lot more useful for us to talk about the frequency of the oscillation, how many cycles is it going through per second, and we know that frequency is given as 1 over the period. And so omega then becomes 2 pi times the frequency. And I can substitute that into here, and I get x equals a cosine of 2 pi times the frequency times the time it's been oscillating. And so either one of these equations works to give us the position of an object in simple harmonic motion if I know either its angular velocity and the time, or I know its frequency and the time. And often we know the frequency. Something that's oscillating back and forth, let's say at 5 hertz, 5 times per second. So those are the equations for position of an object as a function of time. Okay, so having cleared the palette, as you were, let's take a look at finding the velocity. So if we go back to my circle here, you can see that that would be a tangential velocity. So for this object going around a circle at a constant speed, that would be its tangential velocity. It's tangent because it's perpendicular to the radius. And the object right here, its velocity would be right along there, right? And so if we look up here, we see that if we make a triangle, this is the v that we're looking for. And this is the velocity in the y direction, but we're not interested in that because it's perpendicular to the direction we're moving. And so if I just draw this triangle down here again, this is v, tangential, and that's v along the x-axis that I'm looking for. And the angle here is given right here. That's where theta is. So if you look through this if I were to put some axes right there, extend that line out, here's your horizontal, that's theta. And so this angle is going to be complementary to this angle right here, which makes that theta right there. So that's theta. And we see then that V is given as V sub t, the tangential velocity, times the sine of the angle theta. We also recognize that if this is our positive direction, up and to the right, that this is a negative value. So the velocity is V sub t times the sine of theta. Now, looking back at rotational kinematics, we know that the tangential velocity of an object moving in circular motion or moving around a circular path is equal to omega times r. But we know that r is equal to a, so this is equal to omega times a. So that's what I can substitute in here. So v is equal to minus omega times a times the sine of omega times the sine of theta. So keep it in mind that we know that omega, or theta, is equal to omega times t. I kind of got ahead of myself a little bit there. V is equal to minus omega a times the sine of omega t. And like before, we know that omega can be thought of as 2 pi times the frequency. So omega is 2 pi times the frequency. V is equal to minus omega a sine 2 pi times the frequency times the time. And so either one of these will work for finding the velocity of an object that's going through simple harmonic motion. Okay, so now let's take a look at deriving the acceleration of an object in simple harmonic motion. If you go back over here on the circle diagram, you can see that I drew in the acceleration vector of this object going around the circle at a constant speed, and it's a centripetal acceleration. So what I'd like to do now is come over here and draw that vector out here where I can work with it. Let's see if I can do this. So that would be the acceleration vector, and I can see that it has components, a horizontal component and a vertical component. So this would be the centripetal acceleration. This is the A that I'm looking for, which is right here. It's showing that this object is accelerating to the left, and the angle here, if you do the work to figure out what that is, it's right there. And so when we do this, we see that A is equal to the centripetal acceleration times the cosine of the angle. We also notice it is pointing to the left, so it's a negative. So it's minus A sub c cosine of theta. So one of the things that we might recall about a centripetal acceleration is it is equal to the tangential velocity squared divided by the radius. Well, we already know that v sub t is equal to omega r, and that we know that r is equal to a. So in this case, the centripetal acceleration would be equal to omega a squared over a, which is omega squared a squared over a, the amplitude. So a sub c is just omega squared times a. And I can substitute that in here. So the acceleration is equal to the opposite of omega squared a times the cosine of theta. Once again, we know that theta is equal to omega times t. So the acceleration becomes minus omega squared a times the cosine of omega t. And so there's one expression for it right there. Now we can expand this out by substituting for omega. So we get a is equal to minus omega squared times a times the cosine of 2 pi times the frequency times t. And if we wanted to even go crazier than that, we could say that a was equal to minus 2 pi times the frequency squared times a cosine 2 pi times the frequency times t. So those are also expressions for the acceleration of an object going through uniform or simple harmonic motion. Now, something that you'll see in this expression right here, let me write it over here again. We get a is equal to minus omega squared times the amplitude times the cosine of omega t. Now what I'd like to point out here is that if you look up at the expression for x, a cosine omega t is what x is. So this part right there is x. So the acceleration can also be given as minus omega squared times x. And this turns out to be a fairly useful equation for us to use. So we then put that up there. A is equal to minus omega squared a cosine of omega t, or minus omega squared a cosine 2 pi times the frequency times the time. So there are our three expressions that give the position, velocity, and acceleration of an object undergoing simple harmonic motion.